Thank you for the warm introduction, and also thank you to the conference organizers for inviting me here. This is my first time to Germany, and I love it very much. I've been having a lot of fun here. So today I'm going to be talking about how to prove large software projects correct. My name is Gabriel Gonzalez, and I'm a software engineer from Twitter, and the date on this is wrong. Oops. And so let me give a little bit of background of why I care a lot about proving software correct. So I do a lot of open source hobby programming, and I maintain a lot of libraries. But one thing I absolutely hate is that when you put a lot of effort into a library and someone discovers an existential bug in your library that forces you to totally rewrite it or rethink what you were doing or paper over it with a solution that you don't really like. So I like, before I release libraries, to just prove that they're correct. And so that reduces my maintenance burden. I spend less time fixing bugs, more time doing feature requests for users. But I have a kind of an unusual way of proving things correct. So most people, when they think of proving things correct, they'll think, OK, maybe you use a proof assistant, or maybe you use the type checker, which is a form of a proof assistant. But I'm actually interested in proving things correct without even having to use a computer. In other words, I want proofs that can fit on the back of an envelope, or maybe even your head, if it's simple enough. And so what we're going to do is, to make these proofs simple enough that humans can reason about them, we're going to decompose them using the Unix philosophy. So if you're familiar with the Unix philosophy, you know that it emphasizes decomposing complex programs into simpler programs that you chain together. For each of these simple programs, they do one thing, and they do it well. And so we're going to make an analogy to proofs, is that we're going to prove small properties and prove them well. And then we're going to compose these smaller proofs into larger proofs that are relevant to more complex programs. But you can't really compose things together unless they have predictable, reusable, common interfaces between them. In the Unix world, the way they do this is by making everything a stream of strings. You can always connect two things together. Sometimes that connection doesn't make sense, but you can do it. We're going to be doing something similar with proofs, but we're not going to be using strings as an interface. That doesn't make sense for a proof. Instead, the interface I'll be talking about in this talk is going to be using monoids as an interface between proofs, so that we can start chaining proofs together using this particular interface. This is not the only interface you can use. This is just the only one that would fit within an hour-long talk. There's many more interfaces that you can use for connecting proofs together. And if you're interested in that topic, the general terms you should search for are abstract algebra and category theory. They are concerned a lot with how to build highly reusable proofs. So the very beginning of this talk, I'm just going to give a brief overview to the Haskell language. I'm going to be using that as the host language for talking about proving software correct. And then the talk is going to be broken down by the Unix philosophy. In the first part of the talk, I'm going to explain how you take small components and prove them correct. The second part of the talk will discuss how to chain together these smaller components into larger components. And then the last part of the talk will discuss how we can use monoids to make sure that we can compose as many things as possible, followed by a conclusion. So the reason I use Haskell is, first off, it needs to be a purely functional language. Haskell just happens to be the most widely used purely functional language. And also, Haskell is a very concise language, which means that many of these examples can fit on the slides very easily. If you don't know Haskell, that's totally OK. I'm going to teach you what you need to know about the language to understand the proof examples that I will be introducing. So the proof mechanism that I'm going to be using is called equational reasoning. So if you're familiar with proofs, the traditional approach is that first you define some formal language in which you want to prove properties. This language can express equations. And then you create a specification for your program in terms of this formal language. And then finally, you prove that your program satisfies the specification. What makes equational reasoning unique is that your programming language becomes the formal language. You define equations in your programming language, and you prove them correct by using substitutions, again, within that programming language. And so the benefit of this is that you kill two birds with one stone. You only have to learn one language. And as a result, these purely functional languages sort of become gateway drugs for formal reasoning. Programmers who learn them often go off the deep end and get really interested into proof theory. These are otherwise like people who wouldn't have cared about proof or mathematics before. Let me give you a very simple example of equational reasoning. Let's define the properties of the AND operator in terms of two equations. We'll say If I take false and AND it with any other value x, I'm going to get false. So that's equation number 1. If I take true and I AND it with any value x, I'm always going to get back x. So that's equation number 2. Now let's say I want to prove a third equation correct given these two assumptions. So I want to prove that y and true always equals y. I can do this by saying, OK, y can only be one of two possible values. Y is either true or false. So we call it a case split. And so for case number 1, if y is true, then we can use equation number 2 to prove that true and true equals true, which is y, assuming that y is true. And then for case number 2, if y is false, I can use equation number 1 to prove that false and true equals false. Since I proved both cases correct, QED, y and true equals y. Now what's really neat, though, is that this is also valid Haskell code up here. So I can actually take this, paste it into a Haskell source file, open it up in my REPL, and I can now type true and false, and the compiler will deduce that the answer is false. So Haskell is, in a sense, an executable formal specification of a program. And that's why we can reason formally within the Haskell language. Haskell is not the only purely functional language. Some other ones that you may or may not know about: PureScript, a functional language which compiles to JavaScript; Elm, another functional language which compiles to JavaScript; and Idris, which is a more advanced form of Haskell with additional support for dependent types. And all these languages are great if you want to learn more about formal reasoning. If you pick up these languages, you will learn formal reasoning along the way, whether or not you like it. So like I said, Haskell programs are just equations. The way we specify what we're going to run is we equate our program with the main symbol. So main you can think of as a representation of what we will execute. And then we can compile it using the GHC compiler. And if we run it, this example will print hello world, because we equated main with a subroutine that prints hello world. This right here is an example of a type signature in the Haskell language. So the thing on the left of the two colons is a value. The thing on the right of the two colons is a type. So you can read this as saying, puts string line, has type, and it's a function. This right arrow sign means a function. The thing on the left of this arrow sign is the function's argument type. The thing on the right of the arrow sign is the function's result type. So it says this is a function from a string to a subroutine. IO means subroutine. And then this is the subroutine's return value. So if you see two parentheses with nothing in between them, we call that unit. You can think of that as an empty tuple, analogous maybe to void in Java or C. It's just an empty return value. And so this says a function from a string to a subroutine that returns an empty value, unit. Haskell functions are defined using equations. This is a remarkable departure to function definition syntax in most languages. So one way you can read this is saying that this is a function definition for exclaim, saying that exclaim is a function that takes a single argument named x, and then returns the string x concatenated with an exclamation mark symbol. But you could also read it as an equation, saying that exclaim x is equal to x plus this exclamation mark. Equations imply substitutability. Anything on the left-hand side of the equation can be substituted with the right-hand side, or vice versa. Anything on the right-hand side can be substituted with the left-hand side. So here is an example of how you would invoke a function in Haskell. I apply exclaim to the string hello world, and that'll print that. And so this gives me a subroutine which I can equate with main, and then that will generate the exact same program as before, except now with an exclamation mark at the end. Equality implies bidirectional substitution. So anywhere I see exclaim hello world in my program, I can replace the left-hand side with the right-hand side of the equation, giving me hello world plus plus exclamation mark. These sorts of substitution of equals for equals are guaranteed to preserve the behavior of our program. They may change, it may affect how long our program takes to run, but the behavior should still be the same. Vice versa, anywhere I see something plus an exclamation mark, I can substitute from right to left and define it in terms of exclaim. The reason bidirectional substitution works in Haskell is because it is purely functional, which means that evaluation is benign. Evaluation is not tied to side effect order. here are some examples of different variations on functions and subroutines to drive this point home. So even is what we would call a pure function. Really, all functions in Haskell are pure. Really, when we say pure, we mean a function that does not return a subroutine. Even is a function from an int to a bool. Subroutines can have side effects. So for example, they can read things from the console or write to the console or make a network connection. And so getLine is a subroutine that, in this case, will read a line from the console and then return a string, whatever it read from the console. Notice that it's not a function. In Haskell, you don't need to invoke functions to get their side effects. In fact, the only way to get something to perform its side effects is to equate it with main. PutStringLine is sort of a mixture of the two. It's a function that takes a string as an argument, and then it gives us back a subroutine. And if we were to equate that subroutine with main, it would then print the string. Evaluating PutStringLine alone is not going to print the string. Here's an example to make this clear. If I equate x with PutStringLine goodbye world, and then I say equate main with PutStringLine hello world, it'll only print hello world, not goodbye world. Even if I force x to evaluate completely before printing hello world, it still will not print goodbye world. So you might wonder, like, how in the world do I print two things in Haskell? Obviously, it's not by evaluating two things. So how can I actually get two things to happen? How can I equate two side effects with main? And the answer is we don't. Instead, what we do is we provide this operator, which I'll call sequence or and then, which combines two subroutines into one subroutine. So for example, here I can say, here's a subroutine that prints hello world, and I want to combine it with the subroutine that prints goodbye world. And now I can equate that combined subroutine with the symbol main. And if I do that, it will print hello world and goodbye world. And I want to highlight that this sequencing operator is associative. If I combine x and y first, it's the same as if I were to combine y and z first. And because we don't want Haskell to become operator soup, it provides a syntactic sugar called do notation, which desugars to this operator. So if I write do, and I put two commands there, PutStringLine hello world, PutStringLine goodbye world, it will desugar to this operator nested in between them. We can also thread values between subroutines. So for example, I can take whatever line getLine returns, and I can pass it to PutStringLine just by binding it to this string variable. And that will desugar to this bind value, which in this case takes a subroutine that returns an A, a function from A to a new subroutine that returns a B, and then it will fuse them into one subroutine whose final return value is a B. So I can fuse getLine and PutStringLine together to get a subroutine that will read one line from input, write one line to output. Also, what if we don't want to do anything at all, we want a main program that does nothing, we can use return, which you can think of as an empty subroutine. Return takes any value A and gives you a subroutine that has no side effects at all and returns back that A. So if I want main to do nothing, I'll just say main equals return unit. And if I execute that program, it will do absolutely nothing. All right, any questions before I move on to the next segment of the talk about proving small components correct? Excellent. Let's begin with this simple Haskell program. We know that this will print 3 exclamation marks because we call PutStringLine 3 times. That's obvious to us. Now, we don't want to repeat ourselves, so we're going to create a nice function we can use to run this 3 times for us. Haskell people are bad at naming things. This function is called replicateM. It's a function that you give it an action, and you give it an int, specifying how many times you want to run that action, and it will run the action that many times. It's defined inductively. So we have the base case. If I repeat an IO action 0 times, that's return unit, don't do anything. And then if I want to repeat an IO action n times, I call that IO action, and then I will repeat the IO action n minus 1 times. And we'll just assume for the moment that this int is always non-negative for simplicity. So now I can just write replicateM 3 PutStringLine unit, and it will print an exclamation mark 3 times. So we know that this behaves the same as our previous program, but how would we prove that? And we would do it using the equations we defined. So we define replicatem in terms of two equations, and we can use those same two equations in our proof. So let's start from the left-hand side. I want to prove that the left-hand side of this equation equals the right-hand side of this equation. So I'll start here, and I say I'll use the second equation to equate the left, and I'll substitute from left to right. So I will substitute replicatem 3 pushstring line unit with one invocation of pushstring line unit, and now replicatem 2 3 minus 1 to pushstring line unit. And I'll use this equation 2 more times to expand it out. And that'll leave me, again, with the base case here on the right-hand side. And then I can use the first equation right here to replace that with return unit. And then last, I'll use one property, which I haven't proven for you, which is that if you take any IO command with an empty return value and you sequence return unit, it's the same as the original IO command. So I can just get rid of that return unit at the end. I can delete it. And that leaves me now with the right-hand side that I'm trying to prove. This, however, is a really tedious way of proving program is correct. This is not going to scale to large programs at all. For example, if we want to try and prove this, we would have to use 20 equality steps to prove that. So this program says repeat some IO action 4 times. Now repeat that 5 times. So we expect it to be 20 times total. I expect that to be equal to repeating an IO action 10 times, and then repeating that IO action another 10 times. Again, 20 times total. We know that's true. We know both sides repeat it 20 times. How can we prove that quickly and efficiently? Instead, what we will do is we will resort to 4 higher-level equations. I won't prove these for you. Just take my word for it that they're true. I have a blog post which actually goes through and does prove them. And what we'll do is to say, OK, we know this is the same as before. Repeating an IO action 0 times is return unit. If I repeat an IO action x plus y times, that's the same as repeating it x times and then repeating it y times. If I repeat an IO action 1 time, that's the same thing as the IO action. And if I repeat it x times y times, then that's the same thing as repeating it y times and then repeating that x times. And we can also take these last 2 equations and write them in a more point-free form. We don't necessarily need to provide all arguments to the replicatem function. Haskell lets you apply arguments incrementally, partially. So I can say, if I repeat something 1 time, it's the identity function on an IO action, where identity is a function that takes any value x and returns back that x. And if I repeat something x times y times, it's composing 2 functions, repeat x and repeat y, where function composition is the same as mathematical function composition. F.g is a function that takes an x and then returns f applied to g applied to x. And this is a valid Haskell code. And now we can reason about things at a higher level. So we can say, OK, this right here, we can just simplify that to repeating the IO action 5 times 4 times. And we know 5 times 4 is 20. Duh. And now 20 we can split into 10 plus 10. And now we can take this 10 plus 10, and we know that repeat distributes over plus to give us sequence. And now we have repeat 10 and repeat 10. So that's a faster way to prove that these 2 sides are equal. What we've done is we've taken a more complex program transformation in terms of repeats, and then reduced it to a simpler program transformation in terms of algebraic operations on ordinary integers, addition and multiplication. That's going to be a common theme. Similarly, for our original example, if I wanted, I could say repeat IO 3 times. Well, 3 is just 1 plus 1 plus 1. And then I can use the fact that repeat distributes over addition, turning addition into sequencing. So repeat 1 IO, repeat 1 IO, repeat 1 IO. And then I use the fact that repeat 1 IO is just IO. And so that's IO sequenced with IO sequenced with IO. All right, any questions about how you can equationally reason about small components? Because this is what these sorts of proofs we're going to use to prove small components correct. And then I will show you how you can then chain together these proofs in the next part of the talk. So there's actually a pattern to functions that are like replicatem that distribute over operators. So let's assume that we have some associative operator, which I'm going to call plus 1. And associative means that it doesn't matter the order in which that we group things using parentheses. And it has some identity, 0 sub 1. Identity means that it does nothing under this operator. So x plus this 0 gives you back x on either side. And then we have another associative operator, +2, with its own identity, 0, 2. And so what we're going to do is we want to link simple operations using +1 to more complex operations using +2, using some function that bridges between the two. We'll call that function map. And then map will distribute over +1 to give us an equivalent expression in terms of +2. So map of, in parentheses, x + 1 y. We can rephrase that as map applied to x first, then +2 map applied to y. And map also distributes over the identity. So map of 0 sub 1 is the same thing as map of 0 sub 2. Sorry, it's the same thing as 0 sub 2, no map. The reason we use this is because actually lists are a great example of such a map function. So many functional languages provide a map function which transforms a list. So it says, if you give me a list of A's and a function from A to B, I'll apply that function to every value in the list and give you back a list of B's. This is how it's defined. We're not going to really dig into that. So if I say map +1 on the list of 1, 2, 3, I'll get back 2, 3, 4, because we added 1 to every element in the list. And it's called map because it behaves just like this hypothetical map function. We can say +1 is abstractly just function composition. 0 and function composition is associative. And the identity of function composition is the identity function. In this case, actually, +2 will also be function composition. 0 sub 2 will also be the identity function. And so if we substitute these definitions back into our original map equation right here, then we get the equation laws for map, which say that if I map the function f composed with g, that's the same thing as first mapping g over a list and then mapping f over that list. And if I map the identity function over a list, that's the identity function on lists. But this is actually not the only way in which the map function behaves like this. So we can say, now let's say that our abstract map function is the list map function for any function named f. This time we'll choose +1 is ++. 0 sub 1, and so this is associative. This is list concatenation, and that's associative. This right here, 2 empty brackets, that's the empty list. And that's the identity of list concatenation. Same thing for +2 and 0 sub 2. And so now we get this distributing law. So map of f on x's concatenated with y's is the same. So if we concatenate these two lists and then map a function on that, it's the same thing as if we mapped that function over each list individually and then concatenated them. And if I map the function f over the empty list, I get back the empty list. Replicatum is another example of this pattern. Here's our +1, here's our 0 sub 1. This is associative, this is the identity. Here's our +2, here's our 0 sub 2. This is associative, this is its identity. So this is an example of a map-like function. In fact, there's another way. Here is another map-like example of replicatum. So here is our +1, here's our 0 sub 1. Here's our +2, here's our 0 sub 2. And so replicatum distributes over multiplication, and its identity 1. This pattern is extremely common, especially in functional programming. Here's several examples from the Haskell prelude that all exhibit this property. Length distributes over list concatenation to give addition. Replicate distributes over addition to give list concatenation. De Morgan's law is not distributing over and to give or, and distributing over true to give false. Exponentiation distributes over plus to give times, and 0 to give 1. Whether or not a list is empty, null is a function that takes a list and tells you, is it empty? It distributes over addition to give and true, and distributes over the empty list to give true. Put string. So this is a string, something that prints a string to the console without a trailing new line. This distributes over string concatenation to give sequencing. So if I put string 1 concatenated with string 2, it's the same thing as first printing string 1 and then printing string 2. If I call putString on the empty string, I get back the empty subroutine. What we can do then is we can start chaining these equations together to prove larger equations correct. So for example, let's say I have this large expression. So I have not some large expression or with not some large expression over here. I can use the first equation for not, which says not of, oh, sorry, this is, yeah, here we go. Not of x or not y is the same thing as not x and y. So I'm going to apply the substitution from right to left and fuse these two knots into one knot. So I'm going to take these two knots, fuse them into one, pull them over to the right, left-hand side. Now I have a smaller expression in terms of two nulls. So null something and null something. I can fuse them together, pull them to the left, and replace and with list concatenation. Same thing for replicate. So I have replicate here, fuse them together, pull them to the left, and I replace list concatenation with plus. And so now I've simplified a complex operation over larger expressions into a simple operation in terms of just adding two integers together. So that's an example of how you would compose proofs together. But the problem with these previous examples is that this only worked because each one of these things I wanted to fuse happened to have the right type. So their input type, so one of these functions' input type matched the other function's output type. We will not always be so lucky. And so as a result, we don't get a lot of fortunate opportunities to compose things together. So we need some way to provide more reusable interfaces for connecting these proofs together. Are there any questions before I go on to explaining how to do that? And so the way we'll do this is using a reusable interface called Monoid. And if you're not familiar with Haskell, you can define interfaces in Haskell just like in other languages. We call these interfaces type classes. And the idea is that you provide some type, m, and then you define methods over m. So methods that m supports for that interface. So if m is some type that implements the Monoid interface, that means that it provides two functions. One of these functions we'll call empty. I don't like the name. I would have preferred empty. And it says empty is just some default value for m. Like for integers, maybe 0. And mapend is some way of combining two m's together into one m. So maybe plus. The only restrictions on something that implements this Monoid interface is that, we also provide this infix operator, which is equivalent to mapend, just for syntactic sugar. And so the only restriction is that the order in which we mapend values together, it has to be associative. So if I group things like this, it's the same thing if I group things like this. And then mempty has to be the identity of this mapend operator. So this is a pattern we've seen several times before with addition, multiplication, list concatenation, sequencing. So we know that lists, for example, implement this Monoid interface. The empty list is just, empty is just the empty list. And then if you mapend two lists together, that's just list concatenation. So for example, that means I can now use this operator instead of plus plus to concatenate two lists together. So if I say 1, 2 appended with 3 and 4, then I get back the list 1, 2, 3, 4. And if I ask for the empty list of ints, I'll get an empty list. Here's a trivial monoid, actually. We talked about unit, the empty tuple. We can make that a monoid. So mempty is just the empty tuple. In fact, that's the only value. So one thing, let me back up 1 second. One thing that may be confusing is in Haskell, we use the same syntax for both the unit type and the unit value. This is the unit type, and this is the unit value. Sorry if that's a little bit confusing. If I combine two unit values together, well, there's only one possible unit value to get back, and that's unit. And so if I say unit mapend unit, I'll get unit. And then the empty unit is unit. So it seems like a rather uninteresting. Oh, sorry, yes? Does somebody have a question? Oh, sorry, I thought I heard something. So this seems like a rather uninteresting monoid, but we're actually going to start chaining it with other monoids to get more interesting behaviors. Here's a more interesting one. So we can make pairs of values a monoid. This is a two-tuple in Haskell. And so this instance says, if A implements the monoid, so if the type A implements the monoid interface, and the type B implements the monoid interface, then a pair of an A and a B also implements the monoid interface. And so we'll just delegate the monoid interface to the two subtypes. So we say the empty tuple just has two empty fields. And if we want to add together two tuples, we'll just do it field-wise. So we'll add together their left fields, and then we'll add together their right fields. Here's an example of that. So say I have a tuple with 2 lists in it, and I want to add that to a tuple with 2 other lists in it. Then we'll say the resulting tuple's left field will be the first tuple's left field plus the right tuple's left field. Same thing for the right field will be the addition of their 2 right fields. If I ask for the empty tuple of lists, I'll get a tuple with 2 empty lists. And so one thing that's unique about this is we can start chaining instances. So we can start adding monoids together to build more complex monoids. This is a very common thing. Here's another example of building a derived monoid in terms of a simpler monoid. So this says if the type B implements this monoid interface, then any function that returns a B, we don't even care what the function's argument type is also a monoid. And so we'll say the empty function is a function that will ignore its argument and return the empty B. And if we add 2 functions together, that'll be a new function that will take some x, and we'll feed that x to function f and to the function g, and then add their results together. So for example, if I want to take a list and make a palindrome out of that, I can just add the identity function to the reverse function, and then apply that combined function to the list. And so now that gives me a list whose the first 4 elements were generated by this identity function, and the second 4 elements were generated by the reverse function, which just reverses lists. And we know the empty function ignores its argument. So if I say take mempty and apply it to any value, I just made one up, and ask for a list of ints, I'll still get back an empty list. There's one last derived monoid we'll use for our examples. This one says, if the type B implements the monoid interface, then any subroutine that returns a B also implements the monoid interface. So we'll say the empty subroutine is one that returns an empty B. And if we add 2 subroutines together, we will extract their return values and then we'll add the return values together and return that. So for example, readline lets us read any type that implements the read interface. So I'll say, Haskell, can you please read a list of ints from the command line? So I'll type in 1, 2, a list, and it'll return the list 1, 2. I can add readline to itself. That gives me a new subroutine, which will read in 2 lines of input from the user, and then return those 2 inputs added together. And then the empty subroutine, if I ask for a subroutine that returns a list of ints, it will have no side effects, and then it will return an empty list. Now, let's start chaining these instances together. It turns out that the type of the putStringLine function, that's a monoid. Because unit is a monoid, and we said that if unit is a monoid, then a subroutine that returns a unit is a monoid. And if a subroutine that returns a unit is a monoid, then a function from anything to a subroutine that returns unit is a monoid. And so and then what we did is we were chaining together these 3 monoid instances, the first one for unit, the derived one for subroutines, and the derived one for functions. And we can verify that it works. So if I take 2 putStringLine commands, and I add them together, and I apply that to a string, it will print that string 2 times. And it does what you would expect. So there's no limit to how many times we can chain these monoid instances together. So if I have a subroutine that returns 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 unit, that's a monoid. I can add that together. I'll actually show a useful example of why we might want to do that in a second. Functions of multiple arguments are subroutines. And the reason why is because in Haskell, a function of multiple argument is actually several nested functions. So this is really a function that takes a name and returns a new function that takes an int and returns a new function that takes an address and then returns a list of people. I can nest tuples together, and then the resulting thing will still be a monoid. Or I can combine all the above tricks to get really complicated monoids. So let's say I have some subroutine that returns a function that reads a config file, then returns a list of possibly of files that we will read, and each of those files return a bunch of game textures and models. Well, this is a monoid, and I can add these game resource loading plugins together. I'll give an example similar to that also. So Let's give a useful example of why we might want to nest subroutines. This is an example close to my heart because it's related to a project at work. So we deploy a lot of analytics batch jobs at Twitter, and these batch jobs will have phases. So for example, maybe we will generate some files, and then we will package those files, and then we will upload them perhaps to Mesos, and then we'll deploy that job. And then after we're done deploying the job, we may want to log some information. And so what we'll do is we'll model that as nested subroutines. Each subroutine, when it's done, it will return the next subroutine to run. And now if I want to actually run all 5 nested subroutines together, I can just flatten them into one subroutine, which I can equate with main. Here I'll use the join function, which says if you have 2 nested subroutines, you can flatten them into one. And so I want to flatten 5 subroutines into one subroutine. I just apply the join function 4 times. Each time deletes one I/O layer. So you might wonder, why do I want to nest the subroutines? Why didn't I just write it as one I/O action in the first place? And the reason why is because I want to preserve a little bit extra information so I can interleave phases of deploys. So here's a real Haskell program. Let me go down a little bit. Here's the deploy function we wrote. And now I'm going to write a synthetic job generator. So I just give it an integer, and it'll make a fake job that will just print out what phase it's at. So if I give it an integer n, it will say, in the first phase, it will say generating job number n. In the next phase, it says packaging job number n. Next phase, it says uploading job number n, and deploying job number n, and logging job number n. And when it's done, return unit. And what I can do is I can create 3 synthetic jobs, job 1, job 2, job 3, and I can add them together. And this will interleave their phases. So in the generate step, it will do the generation for all 3 jobs. Same thing for the packaging step, uploading, deploying the job, and logging the job. This is why we wanted to preserve the separation of phases between them. Now you may wonder, why didn't you just store it as a list of subroutines instead of nested subroutines? The reason why is because I can actually, each nested subroutine actually closes over values bound in previous subroutines. So if I read something in from if I had some side effect, which read in some value from an external source, downstream subroutines could reuse that value. I could just thread it directly to here. I don't need to do any complicated information passing. It's already in scope. And of course, as you'd expect, if you deploy the empty job, the empty nested subroutines, again, nothing happens, exactly like you would expect. And I know right off the bat that this addition of jobs is automatically associative. So I know it doesn't matter in which way I group things. And if I add a job to the empty job, I'll get back the original job. And we can easily prove correctness just using induction. We just say, unit is a monoid, therefore this is a monoid, therefore this bigger type is a monoid, therefore this bigger type is a monoid, and so on. This sort of induction is very easy for humans to do. You can do it in your head very easily, and the compiler will check it for you. The compiler will just tell you, if you try to add it together, the compiler will allow it to type check if there is a monoid instance, and it won't type check if there's not. Let's use one more example, concrete example. So let's say I want to have several outputs for, let's say, some terminal driver. And so this will be the type of a particular output that we may want to register. So this will be some subroutine that will acquire some resources, maybe like open up a file handle. And then it will return a tuple with 2 values. The left value is how we're going to handle characters that the user types in. So we'll run this function once every time the user types a character. The right-hand value will be a subroutine that will free the resource once we're done reading input from the user. And so our high-level driver function will just acquire whatever handle there is, and then it will do a loop. You don't need to understand this code in detail. Just take my word for it. And then we'll just go over the user's input in a loop, apply our handler function each time the user types a character. And then when we're done, it will call the finalizer that we registered. And so what's really cool is that this type right here is a monoid. Because unit is a monoid, therefore I/O of unit is a monoid. This unit is a monoid, therefore I/O of unit is a monoid. Therefore, a function from a character to an I/O unit is a monoid. Since the left element of the tuple is a monoid and the right element of the tuple is a monoid, the whole tuple is a monoid. And since the whole tuple is a monoid, then any subroutine that returns that tuple is a monoid. So we can start adding together these input handlers. Let's define some example handlers. So here's something that just writes to the console. This doesn't need to acquire or finalize any resources. So we'll just say the acquisition step will do nothing. It'll just return our tuple. And then our handler will just print whatever character the user types to the console. And then the finalizer will just be the empty subroutine. I can just write empty. That's equivalent to return unit. So that's not a very interesting one. We can do file. So this will be something that writes out to a particular file. So we give it a path that we want to write out to. And then what it will do is it'll open that. So as the acquisition step, it'll open the file, store its handle in this handle variable. And then it will return first our handler, which will print characters to that handle. And then here will be our finalizer. Close that handle when you're done. And then finally, we can do counter, which will actually not print anything out to console or a file. It will just print out how many characters you typed. Every time you type a character, it will just print out a new number. And so the acquisition step will acquire some mutable reference. In Haskell, we call this IOREF, starting at 0. And then we'll define a handler that every time we type in a character, it will just read our mutable reference, print the value. In this case, maybe it starts at 0, so maybe the first time it'll be 0. And then it will store n+1, the mutable reference. So the next time that we read from it, it'll be an incremented value. And so this will have no finalizer because there's nothing to finalize. And so we store that handler as the first value of the tuple. So let's say I want to write to the console and the file test.txt and the file test2.txt. So if I run this program, then what it will do in the first step is it will acquire both these handles. And then it'll register this handler function, this handler function, this handler function. It will combine them together into a single handler function. Every time I type a character, it will write out to the console and this file and this file. And then when the program's done, it'll finalize these two files correctly. And we did that just by adding together these three syncs. It was as simple as that. This is very easy to change. So let's say I don't want to write out to the console anymore. Instead, I just want to print out the counter. Then all I have to do is just delete this console and then add in this new counter handler right here. And then it's as simple as that. It's very easy to add and remove plugins this way using this Monoid interface. All right. How much time do we have left?
10 minutes.
10 minutes? OK. So I leave 10 minutes for questions? Because I have a longer version of this talk. So depending on how many questions we have, I can do one more section. Would people be interested in one more section? Yes. OK. Let me open it up really quickly. Give me just a second. Oh, damn, don't tell me I don't have it. I think I do, actually. Hold on. Nope. OK, then I will just improvise really quickly. OK? Sorry. Yeah, I should have. Well, I should have sent the longer version. All right. So it turns out that all the derived Monoid instances we gave were actually special cases of a more general Monoid instance, which was this. So there is an interface which I will not go into too much detail into, which is called applicative. And so we can actually, all the three previous Monoid instances that we wrote were actually just special cases of that more general Monoid instance, including the tuple one. It doesn't seem like it, but it actually is. And the reason why is because there are three applicative instances that look like this. This is not quite legal Haskell, but close. Sorry. So applicative is a reusable interface. It's another one of these reusable interfaces I talked about. And so what we can actually do is that if we prove that anything like I/O or functions or tuples implements this applicative interface, we can automatically derive what's the appropriate lifted Monoid interface together. Because the applicative interface obeys laws, just like the Monoid interface does. And those laws guarantee that these two equations right here are guaranteed to automatically generate a correct Monoid instance, which is still associative and still has a correct identity. This is a very abstract way of generating correct Monoid instances together. And it actually ties in very into the original portion of our talk. So I will just go to the pure function just for a second. So what's neat about the pure function, it says if f is some applicative, then pure is a function that will take an a and give you back that a wrapped in f, right? So like if f were IO, then that would be giving me an a and return me an IO that does nothing and returns that a. And in fact, it turns out for IO, it's the same thing as the return function. For functions, it says if you give me an a, I will give you back a function that will ignore its input and return an a. That's called pure. That's also pure. For tuples, it turns out that that for tuples will just be the empty tuple. This is not correct. If you give me a b, then what it will do, it will give you back a tuple whose, if you give me, no, b. So if you give me a b, it will give you back a tuple whose left field is empty and whose right field is b. So pure is a function from b to a of b, where a is empty. OK. And so pure is actually a map-like function. So pure lets us bridge from a more complex thing to a simpler thing. So the right-hand side of the pure, like the subroutine or the function or the tuple, is the more complex part. The left-hand side is the simpler value, just like the a that wasn't wrapped in anything. And pure obeys these two map-like laws. If you do pure x added with y, it should be the same thing as pure of x added with pure of y. And if you do pure of mempty, you just get back mempty. So this, again, pure is like our map function. This is our +1. This is its identity. We know this is associative. That was the requirement. This is the identity of mappen. Here's +2. Here's our 0 sub 2. And pure distributes over monoid and mempty, just like our original map function. So this is a very abstract and general interface that we can reuse for building complex proofs together. All right, so now going back to the slides. Okay. So we said that what we're going to do is we're going to build small components that are simple to prove correct. So these are small components like IO and functions and tuples and lists. And these would sort of be, we're making the analogy to Unix, these would be equivalent to the simple Unix utilities like word count or head or grep or cat. It's easy to verify that the individual components are correct. They're easy to build. And then we can start chaining these things together to build more complex systems. We build larger, so in the Unix world, we build larger components by piping together smaller components. In the proof world, we build larger proofs by chaining together smaller proofs. And we know that composition of proofs will preserve correctness. And we provide a reusable interface. Monoid was the first example. Applicative is the second example. Didn't have a lot of time for that one, unfortunately. And each proof, and just like each Unix utility takes a stream of strings as its input and produces a stream of strings as its output, each of our proofs is going to take a monoid as its input and produce a monoid as its output. So we can just connect them end to end. And Monoid is not the only reusable interface. Unlike Unix, where everything is a string, actually there's a lot of other reusable interfaces other than Monoid, in not just in the Haskell world, but in the mathematical world. Because you can think of mathematics as all about reusable interfaces, and the study of that is abstract algebra and category theory. So if you learn a little bit more about those areas of mathematics, you'll learn lots more techniques for combining proofs together to build larger proofs. In fact, those areas are so abstract that they're often called generalized abstract nonsense, just because they promote a little bit too many. Sometimes you don't really understand what's going on at all until you see several more specific concrete examples, because they're too abstract at times. And that's the end of my talk. I blog a lot about this sort of thing, equational reasoning, proving high-level things correct. If you'd like to learn more, just visit my blog at haskellforall.com. And if you have questions and you just want to ask me about Haskell or programming or math or equational reasoning, you can always reach out to me on Twitter. My Twitter handle is GabrielG439. And unless you have any other questions, I think that's the end of my talk. Yes?
You started out by talking about how you use Haskell data to do
So actually, the truth is, at Twitter, we do this a lot in Scala. So Scala is not a purely functional language, but it's close enough that you can sort of get away with this as long as you stay away from like impure bits in these proofs. So we actually use concepts from abstract algebra all the time. I think there's a Scala library for this called Scala Z. We don't use that at Twitter yet, not for any particular reason. We actually have our own library called Algebra, which has some overlap with Scala Z. We use it a lot in analytics all the time. So it turns out that properties like associativity and emptiness are fantastic for MapReduce jobs. It makes it easier to parallelize things and to build more complex MapReduce operations from simpler ones. Like that applicative interface is fantastic if you want to compute two things at the same time in a single pass or a single MapReduce step. It's fantastic for that. So we do actually use these interfaces heavily at Twitter, even in an pure language setting like Scala. So it is somewhat transferable if you restrict yourself to a subset of the language. Yeah.
How much work do you have to do that restriction, and how much thought do you have to put into working out exactly what those restrictions mean?
I mean, generally the rule of thumb is like if you proved it correct in Haskell and you translate that to Scala, like people consider that good enough. I mean, if you stay away from mutable bits, if you start doing doing mutation for efficiency, you got to like stare at it harder, and then you have to and it's harder to convince yourself the mutation's correct because it's more difficult to equationally reason about mutation as opposed to like purely functional ways of doing things. So you just sort of like have to to be honest, I don't know that much about proving mutable code correct. So I don't know exactly how you would do it, to be totally frank. But that's why we try to stay to purely functional idioms as possible. Our rule at Twitter is be functional by default and only optimize for mutability when you really need it. Oh, yeah?
I just noticed you used an IRF in one of the examples, which then is mutable, so how is that?
Oh, yeah, that's the cool thing about Haskell is that, so let me clarify. So the difference between a purely functional language and an impure one is not whether or not things have side effects or mutation. It's whether or not evaluation triggers it. And so the reason why that distinction is important is that when you're doing equational reasoning, you're substituting one expression for another, you're changing the order of evaluation. So if side effects are tied to evaluation order, you're changing the behavior of your program. In Haskell, because side effects are not tied to evaluation order, these sorts of transformations don't screw up the behavior of the program. So the order there will be mutation, but you know the order of mutations will be the same, even under these equational transformations. That's the key trick that makes this work. Yes? Okay.
I think one question is okay.
Okay. Yeah.
I mean, you talked about real-world libraries that you worked on, and then you have these very elementary examples. So, kind of, what is the kind of real-world application of these things?
So, if you want to see a much larger example that uses these principles. I have a library in the Haskell world which is called MVC, stands for Model View Controller, and it shows how a lot of concepts from Model View Controller idiom can be expressed in terms of these abstract algebra interfaces. So that's a much larger example. My pipes library, which is a very large coroutine library in Haskell, uses a lot of interfaces from abstract algebra to prove correctness. And then there's another library I have, which is just for shell programming, which is just about like the messiest, ugliest thing you could possibly do. And that actually has lots of interfaces from abstract algebra. And that library is called Turtle. So those are probably the largest examples I can give you if you search for those.
What exactly did you prove there?
Let me give, how many minutes? Can I have a few minutes? Here's an example from pipes, okay? So another quick impromptu example. You have a generator library, right? So the generator has things such as for and yield. And so here's an example of some laws that you would expect to be true for a generator. So for example, you say, if I loop over some generator that yields a single x, that would be the same thing as just applying f to x. And similarly, if I loop over some generator, g, and for each value of that generator g, I yield an x, and that's the same thing as just getting back the original g. And then, if I loop over some generator, I'm going to call it, g, with some function f1 and some function f2, that's the same thing as first looping over g. For each value of x, looping over f1 of x and applying f2. Sorry, that won't be a little bit harder to follow you, but if you think about it, it's correct. And so it turns out that you can actually rephrase these three equations in terms of another operator. So we'll call this operator this. And we'll say this operator is equal to for f of x, g. Notice how similar that looks to function composition. And then we can rewrite. It turns out that these three rules at the top can be expressed in terms of three equations that are more like abstract algebra. The first one would be yield into f equals f. So that's an identity law. The second one would be f into yield equals f. That's another identity law. And the third one is equivalent to saying that f into g into h is the same thing as f into g into h grouped differently. So often things that look like they don't have abstract algebra interfaces can be reformulated in terms of things that do. And then you can prove these laws and then just map them back using equational reasoning to these more practical laws up here. You just have to see lots of examples just to convince yourself that this sort of thing scales to more complex systems. I just picked the examples that could fit within the talk without having to introduce a lot of other types and interfaces.
Okay, well,
Yeah.
thanks for the talk.
Yeah.